Okay. Hi to all. So you people can hear me?
Yes, we can hear you. You only need to start the recording, sir.
Yeah, sure, I will. So we are live now.
Yes, in YouTube and Facebook.
Okay. Okay. Let me check.
Ya, ya te lo pagué. Ven. Ten, sácale este, mira. Este, bebé. Mira, este que no tiene punta. Aquí sí. Ahí va.
Okay, guys. So how many people are here now? So it's a new member here, Nargis. Can you hear me, Nargis?
Yes, sir, I can hear you.
Can you please introduce yourself?
Yes, so my name is Nargis Kapoor and I am a graduate student from Center for High Energy Physics, Punjab University. Researcher is a big word to be called. I am just a beginner for the research and I just wanted to know about the laser in very briefly. That's it.
So what is your background actually?
My background is a theoretical side of physics, high energy physics, particle physics.
Okay, so
I have done BSc double math physics first.
okay.
Math and physics background was there. Then
Okay.
I had computational physics and now high energy physics.
So, but why are you interested in laser?
Because I'm switching my research side to the experimental side. And there was a professor of mine. He said to me, laser is a technology, so you should take interest in it. So I just saw your profile on Professor Bilal Masood profile. So I was like, it seems like you are doing some kind of very interesting work. So I wanted to dig in. That's it.
Okay, sure. So I
Thank you,
hope
sir.
you will enjoy. But the thing is that you have to follow my previous lectures. So
Yes, sir,
otherwise,
I'm doing it.
yeah, otherwise you may have a problem to understand some of
Yes,
the.
I took first 2 3 lectures. So there was not the things that they are kind of alien to me because I have very precise physics background, in especially the double math physics. So
Okay.
okay, these things are not being tough for me for right now.
Okay.
What comes next, I don't know.
Yeah. Okay, but I mean, if you try, you can learn definitely.
Inshallah. Thank you.
Okay, so David, you are there.
Yes, I'm here, sir.
So it's live on everywhere, isn't it?
Yes.
Okay, guys. So I don't know how many people are here. Maybe slowly they will come. So what was in the last lecture? What we studied in the last lecture? Amna Sail.
Sir, we studied about optical resonators, the amplification and gain.
Okay. Okay, so in this lecture, today we are going to study the remaining part of the cavity optics and about the laser modes. So the laser modes, I mean, it may take one more lecture probably, and the cavity optics will be finished today. So the laser modes, basically, it's the beginning of ultra-fast stuff. Okay, so let's start now. So this slide you people must have seen in the previous lecture as well. This is for you people to understand some basics of optics. Basic of a curved mirror, actually. So like concave or convex mirror. So I don't need to explain here. You people just need to go through and that what is C here and what is the F here, what is R, radius of curvature. This is center of curvature. This is the focus point. And there are two kind of mirrors, like convex mirror and the concave mirrors. So diverging, converging, and these things are important, but because when we make the cavity, we need to understand the curved mirrors. Okay, so excuse me. Resonator, you know already. I don't need to go back. When the two mirrors are placed face to face, we call it a resonator or cavity, and the medium, the gain medium, the laser medium, in between two mirrors. So there are kind of three things if you recall your memory: pump, gain medium, and resonator. So the gain medium comes in between the resonator mirrors, and the pump from outside, it depends. First thing is that even if we use two mirrors, okay, but there may be a different kind of configurations. So to have efficient laser action, okay. So for efficient laser action, we need to study a few different kind of configurations and the stability of the resonator. So the stability of the resonator, there is a certain criterion for it. And this criterion is here. You can see that this formula G1 and G2. So length of the cavity and the radius of one mirror and radius of the second mirror, and the L is the length of the cavity, like you can see here. Okay, so if the product of, if we multiply G1 and G2, and if the value comes in between, then like it should be greater than equal to 0 or less than equal to 1. So in between 0 and 1. So we can say that this cavity is stable. Even 1 is okay, even 0 is okay. On the edge, but these are okay. So this formula is a key formula to find out the stability of the resonator. And we will see in the coming slide that what configurations can be. And we may need to calculate, you may have some problems to solve this and to find out the G1 and G2. And these will be like simple calculations, length and radius of curvature. But keep remembering one thing, that in case of a convex mirror, the radius of curvature is always negative. Okay, and in case of a concave, it's positive. Whenever you solve the problems related to these, so you should keep it in mind. Okay, first simple kind of resonator, that configuration, you can call it Fabry-Perot resonator or plane parallel cavity. Okay, plane parallel cavity. So plane parallel cavity means there are two parallel mirrors. Okay, two mirrors parallel to each other. You can see here. And here somewhere will be the gain medium. Okay, and like you can see here in this animation. So these plane mirrors are reflecting type definitely. So the light is traveling to and fro between these two mirrors, and it passes through the gain medium. So it has some advantages, it has some disadvantages. Okay, so like you can see, there are some points here. First thing is that these mirrors are supposed to be extremely parallel to each other. Okay, if they are, or if one of the mirror is not parallel to the other, so it means it will be misaligned, and misaligned means there will not be a laser action. So it's like very sensitive. You have to be very precise with these two mirrors. You can see the point here. So like if the mirrors are not aligned precisely, so the beam maybe it may bounce one or two times and will go out. This is efficient until and unless the mirrors are very well aligned. Okay, the light pass through the gain medium. Okay, so it means like whole of the gain medium area is covered by the light. Okay, so it use like maximum use of the gain medium. Okay, so if these are like plane mirrors, these are not curved mirrors. So if these are the plane mirrors, it means that there is no focusing. Okay, so the light will be parallel between these two mirrors, and the gain medium will be in between these two mirrors. The light passes through, the photons passes through the gain medium, the laser medium. So it will be amplifying the photon successfully, but it has a disadvantage. Why? Because misalignment, it easily misaligns, or you need some certain techniques to align it properly. Okay, and to align it properly, this is not a topic of today, how to align it, just giving the introduction to what kind of cavity. So there are certain techniques actually to align this kind of critical things. Okay, so the main disadvantage of this cavity configuration, that the misalignment, it can easily misalign, it has to be extremely parallel to each other. Okay, now move to the second configuration. Before to move to the second configuration, let's see the stability of this one. It's a weak instability or on the edge. So you can see that the R1 and R2 are infinite. It means they are not focusing the light anywhere around. Okay, and these are plane mirrors. So if we use the formulas which we have just seen 2 slides before, that the G1 and the G2. Okay. So L over R1, R is infinity. L over R2, R2 is also infinity. So L over R1 and L over R2. Okay. So definitely these are 0. So you have 1, 1. So the product of G1, G2 is equal to 1. Still, it is stable, but it's on the edge. So it's not that much stable, it means. Okay. So stability is marginal kind of stability. And marginally, I mean, you can keep it in mind that it's really difficult to align. Okay. And it can be misaligned in, I mean, like sometime with a little touch or something like this. So this kind of configuration is not very common in practical laser building. Okay. Okay. So other configuration here, that is concentric resonator cavity. Okay. Concentric. So it means there are some kind of curved mirrors are used. You can see here curved mirrors. Okay. So these are basically concave mirrors. Okay. In this configuration. It also has many disadvantages and advantages as well. So first thing is that in the previous one, your length of the cavity, you can calculate according to the requirement, like what wavelength at the output do you want. As we studied in the last lecture. Okay, so here, this length actually, in this case, the length between the two mirrors, the length of the cavity is equal to 2R. So 2R means twice the radius, okay? So if you see on the corner here, this is R. Okay, if this is a curved mirror, this is the R here and this is the center of the curvature. This is the radius of the curvature. Okay, so it means it has 2R, so R and R. So 2R, total length of the cavity is equal to 2R. And the cavity, the center of the cavity, the center of the cavity, it means is coincide with the center of the curvature of both the mirrors. C. We see here somewhere. Okay. Okay. So it means that the beam waist is located at the center of the cavity. Okay. The beam waist. Beam waist what? Where you have like, you cannot say it's exactly focused. It's a waist where the beam width is minimum possible. Like there is certain possibility. So, but this is a possible minimum. And in this case, one of the disadvantages you can also observe here in this animation, that the light concentrate here, center, and most of the gain medium is empty. I mean, it's not passing through. The photons are not passing through most of the gain medium. So it means it's not efficient. Okay. So to take out, I mean, to have a maximum efficiency, we need to utilize the whole area of the gain medium. So here the whole area of the gain medium is not utilized. So light is passing through, but on a small portion, only through a small portion. Okay. And that is why it's written here, the filling is poor. And this one is also very, very sensitive to the misalignment. If just a little movement in the mirror, then you will lose the laser action. Okay, because it will not concentrate here. If the cavity is moved, then it may concentrate here somewhere, like this. So it's very sensitive. Now, to check the stability of this configuration, this is the formula here. Okay, so the R1 is equal to L1 and L by 2, and R2 is also equal to L by 2. So because if C at the center of curvature, and this one is R, this one is R here, okay, and it means this total length is L. So it means that this R is equal to L by 2, and this one also R2 L by 2. Okay, so if we substitute these values here, then definitely what we get, -1 and -1 here. Okay, L, this one will be cancelled out, and the product we get 1. It's similar like in case of plane parallel mirrors. So marginal stability, okay, on the edge. Not very efficient, not very commercial. In commercial kind of laser, I mean, you cannot use this configuration because it will be misaligned easily. And if it is misaligned, then the layman or the user may not be able to align it again. So it's not very useful and not very productive. Move to the third one. Confocal resonator cavity. Confocal resonator cavity. Okay, so just a minute. Okay. Okay, so this one is confocal resonator cavity. The length between the two mirrors here, L as usual, okay, but this L here is equal to R, radius of curvature, okay. So there are two mirrors, M1 and M2 of same radius, R, okay. Like here you can see, this is and this one. It means the focal length of the mirror is L by 2. Okay, if you see here, L by 2, and the center here. So this is L by 2 from here, L by 2. Okay. So length of the cavity is L, but R, which we needed in the stability formula, radius of curvature, is equal to what? Focal length. Focal length actually, if you see here in this diagram, that is why you need to understand. The focal length here is a midway between the center of curvature and the pole. Okay. And according to this figure, what you see, F is equal to, sorry, F is equal to 1 over R, focal length. Okay. And these beams are focusing here. Okay. So if these are focusing here, it means this is a half of the cavity, which is L by 2. L by 2. Okay. And radius of the curvature is this one. Okay. So the radius of curvature is equal to length of the cavity actually here. What is the advantage here? Still, it's not very much advantageous. Like first thing you need to know why it is called confocal. Okay. And because the focal point coincide with the centers, focal point, the focusing. Okay. So that is why it's called confocal. And it's easier to align as compared to the previous two, but still it focuses at the center, and a little bit misalignment, you may not get efficient lasing. Till the small portion of the gain medium is utilized. Okay. Filling is poor. Okay. Now we check the stability of this system. Better than the previous one probably. So G1 here, L1, we call it 1. Can be 1 centimeter, can be 1 meter. Okay. And or you can say L over L. Same thing. So let me write here, G1 is equal to 1 L over R1. So it will be L, and the radius of the curvature is also equal to L. So it cancel out. So if it is cancel out, then definitely answer will be 0, and similarly answer will be 0 here. The product will be 0. Still it's marginal, it's on the edge. It's on the edge. Better to have in between 0 and 1. So to satisfy this criteria, still it comes in this criteria, but it's not that much stable, which is supposed to be. You can see here, this is a confocal kind of cavity. And this one here, it shows that how it is misaligned. You can see this mirror, it went a bit down, and then you get things misaligned. Okay. Still not very useful. It depends what kind of the laser medium is used. If the laser medium with a very high gain, then we may use this technique, but still not very useful because of very small portion of the gain medium is covered, is filled with these photons. So efficiency will not be that much. And second, also the misalignment problems. Move to the fourth one, hemispherical cavity, or the plane and spherical resonator. So you can see in the diagram here, hemispherical cavity. Okay, one side you have a plane parallel mirror, other side you have a curved mirror. Okay, and the length of this cavity is supposed to be like this. The radius of curvature of this one is equal to the length L of the cavity. Okay, so L is equal to R. Here is written, but it is, I mean, whether you write capital or small letter doesn't matter. So this is hybrid kind of cavity configuration. Hybrid kind of cavity configuration in the sense that you have a plane, the plane parallel mirror, and other one is spherical or the curved mirrors. And definitely the curved mirror has to be concave mirror, okay, so that the light can be focused on the other side. Now, in this case, if this is R, so light will focus somewhere in between. Okay, these rays are showing that these are the radius of curvature. Okay, and the radius of curvature of the curved mirror, of the concave mirror, at least equal to that, the length of the cavity, or little bit more than that. Okay, and usually it's larger than the cavity length, the radius of curvature of that concave mirrors. Okay, it's okay to have a larger little bit, or at least equal to the length of the cavity. And if you see here, the gain medium is covered a lot in this kind of configuration. Okay, so filling is good here. So the gain actually here we have to see, I mean, we have to adjust the gain. We can move the gain medium whether towards the spherical mirror, the curved mirror, the concave mirror, or towards the plane mirror. Okay, and it depends. I mean, if you want to increase the efficiency, you can move this gain medium probably towards the curved mirror, so that to have better filling and to be more efficient. And if the gain is too much, it may cause problems sometime. Then you can shift or move this gain medium towards the plane parallel side. Okay, so in this case, pretty stable. It doesn't have much problem of misalignment. You can see the configuration. Even this concave mirror, it moves a bit, but still the light will pass through, or the photon will pass through the gain medium. And even if the plane parallel also tilt a bit, still the light will pass through the gain medium unless they are misaligned completely. So little bit misalignment is it can be compensate in this kind of configuration. Okay, so to test the stability, as I mentioned that the radius of the spherical mirror is at least equal to the length of the cavity, or sometime much larger, it depends. But at least has to be equal, minimum requirement. So this arrangement is very popular and very commercial. Popular and commercial in the sense because it's not very sensitive to misalignment, and it can be used in many places, and even layman can use it. Okay, so even if it is misaligned a bit, but still it will work. So if we see the G1 here and G2 here, L, length of the cavity, okay, L is the length of the cavity, and R. So in first case, we are considering that R actually is a little bit more than the length of the cavity. Okay. So that is why R here in this example is 1.5 L. Or if you put R1 is equal to L, this is also possible. Okay, but in this case, it will go to the edge of the stability. Okay, and because the product will be 0. So better to have radius of curvature a little bit more than the length of the cavity. So it doesn't matter. I mean, the efficiency will be higher because the filling of the gain medium. So G2 obvious, and the plane mirror, it has infinite radius of curvature. So we have 0.3 here, 1 here. The product will be like 0.3. So in between 0 and 1. So it's very good stability wise. But the condition is that the radius of curvature of this concave mirror has to be more than the length of the cavity. Okay, more than the length of the cavity. Okay, so if the radius of curvature, I mean having length more than the cavity, so then it will focus somewhere here. Somewhere here, it depends. Anyway, so this value this one is 0.3. So in between the 0 and 1. So it's a very good option to use this kind of configuration. As I mentioned, it's the most popular in the commercial system because it's not easily misaligned. If you don't, I mean, apply so much force on the sides of the mirrors or something like this, and it may not misalign easily. So second point here, you can see this arrangement is the most popular for low and medium gain lasers, which is one of the example is helium neon laser and argon laser. So if you could see my previous lectures, I have shown the helium neon cavity as well and helium neon laser as well. And argon and laser, I didn't show the cavity, but we discussed a bit. Commercial laser. So it's very good for the commercial systems, okay, because it's insensitive to the misalignment. So this kind of configuration is used commercially, okay, and usually the laser output come from the plane mirror side. If you remember, in the cavity, one mirror is always partially polished, which we call OC, output coupler. Okay, so the output is coming from the plane mirror side, and helium neon, you must have seen, or you can see in my previous lectures, helium neon enclosed in a kind of vessel or container or a cylinder, and they have this kind of configuration. So if you see the helium neon laser, I mean, it goes without misalignment years. And mostly it is used roughly in the labs because undergrad labs, I mean, the helium neon laser is pretty common in undergrad lab. Okay. Here in this point, they have mentioned that OC, output coupler, is spherical. It entirely depends on the laser medium. But most of the laser, or many lasers, they have a coupler on the side of the plane mirror. But it depends on what. If the radius of the curvature, I mean, if it is more than the length of the cavity, then probably we need to take the output from the curved mirror size. But if it is equal to the length of the cavity, then probably we can take it from the plane mirror side. Okay, so now move next. Long radius cavity. We have two concave mirrors, but the radius of these concave mirrors are very long. Okay. So it means the light may not focus at the center tightly, but little bit away. You can see in the animation somehow, you may get idea. So obviously we are using the two mirrors, which are concave mirrors. And the radii of the curvature significantly longer than the length of the cavity. Okay. And both the mirrors should have equal radius of curvature, okay? But it has to be greater than L. Okay. So here you can see like more than outside of the cavity. This is very good arrangement. And it's very insensitive to the misalignment. Like the light pass through, light is not focusing here in the center of the material, gain medium. And it will be like filling up. It's filling up the gain medium very nicely. In the animation, it's not, I mean, it's not showing 100% how it could be, but give a little idea about it. So it will, radius of curvature is outside somewhere here, and it may focus here somewhere, the light, or here. So it means the gain medium will be here, and it's very much nicely filled. So we have efficient cavity configuration here. And this is stable, as I mentioned, insensitive to the misalignment. And light can bounce to and fro, back and forth indefinitely. Okay. And this is also very common in commercial lasers, this arrangement. Because commercial laser means a user or a layman, he or she, they cannot align it every day. They don't know. So it works years without misaligning. Okay, if it is misaligned, definitely you have to call to the technician or engineer to do it. But previous arrangement, spherical and plane, and this arrangement, long radius cavities, are very much beneficial for the commercial lasers. And it works fine, and it has a very good efficiency. Okay, other configuration here. Some other configurations are also there. These were the main 3-4 we discussed. Concave, convex cavity. One side you have a concave mirror, other side you have a convex mirror. Okay, converging, diverging. You can see here, this is your concave side. Okay, and this one is your convex side. Okay, and this one is your gain medium here. Okay, convex doesn't mean that it's too much convex. Little bit curved, little bit curved. What is the advantage of this one? The gain medium is filling up properly. Okay. Gain medium is filling up properly. And also it's insensitive to the misalignment because light from the convex side is spreading. So even if it is like tilt a bit, so even in this case, it will pass through the gain medium. So the misalignment may not affect much the efficiency. It does, but not much. So it's very good and efficient. And if we want to find out or to calculate the stability test here, we can have here, you can see G1, we assume some values. Length of the cavity, we say is 50 centimeter. Okay. So the L, 50. And the radius of R1, in case of a convex, we take the minus. Okay. So this one we are considering is R1, and this one we are considering is R2. Okay. So 500 centimeter radius of curvature, and this one is 100 centimeter radius of curvature. Okay. So if you calculate this one, 1.1, if you calculate this one is 0.5. So the product is 0.55, exactly in the center of this criteria, in between 0 and 1. So it's a perfect choice to have this kind of cavity. Okay, so that is the one of the benefit of this cavity. So we have studied some the cavities, the cavity optics, the configurations, and now we move some examples which you can solve in detail. This is a similar kind of example which I solved in the next the previous slide. Okay, this is concave convex probe. So this is similar. Okay, and you can try by using the different values, so that this one is not negative, this one is positive. Okay, so one problem always here is not working properly. So here, this R2 is 100 centimeter. It's positive. Okay. So if you calculate these, you can find, you can have different values. Maybe in the assignment, I may give you a different values, but it depends. You can practice by yourself how to calculate the stability of the cavity. It's very important, simple cavity. This is a simple cavity. Okay. In case of ultrafast laser, the cavity is not that much simple. Next example. This is the example of unstable resonator. So unstable resonator means the cavity is not stable. If it is not stable, it means the efficiency will be poor or maybe zero efficiency in some cases. So you have two concave mirrors, and R1 and R2 30 centimeters, okay. And length of the cavity is 90 centimeters. This is kind of concentric probably. And if you calculate, the value comes, the product come actually 4. because G1 and G2, they are same. 4 means out of this. So it's not less than equal to 1. It's greater than 1. So definitely this cavity is unstable without any question. But we may need some unstable cavities in some of the laser configurations. Okay. It may be surprising for you, but we also need unstable cavities. If the laser is very efficient, the gain medium has very high gain, probably we need to have unstable cavity. And unstable cavity means that it has to be that cavity will not be working forever, maybe. And that cavity may not have a partially polished mirror, maybe. Okay. So here, unstable resonator configuration. There are two kinds of unstable resonator configuration, the popular one, the commercial one, and in a military kind of lasers, defense lasers, where we need very high power, unstable cavities can be used or is used actually. So what you see here, the popular option in certain high power lasers. Certain high power lasers mean that can be carbon dioxide laser is one of the highest power. But we have other high power lasers as well. It's saying about the gas lasers. Okay. We have a diode lasers, very high power diode laser, fiber lasers, we have very high power, but that is a different technique actually. So this is like a excimer laser. Excimer is also gas lasers, and the carbon dioxide laser, both are the gas lasers. And two categories of unstable resonator you can see here. This one, positive branch confocal resonator. Second one, negative branch confocal resonator. You can see in the figure, if it is not clear, in the next slide, the figures may be more clear. So in a positive branch confocal type, you use one concave mirror, okay, and on the other side, you use a convex mirror, but smaller in size as compared to the other mirror of the cavity. Both the mirrors are fully polished. What is happening here? That after certain round trips, the light came out, the laser light comes out, and we have output beam, but this light is coming out not through the mirror, but around the mirror, because this mirror size is smaller than the one side. So the light will definitely come out because this size is bigger, but this light is coming out from around surrounding areas of the other side of the mirror. So this, the beam shape, it's called annular shape, okay? Hollow from the centers, donut. But I mean, you cannot focus to pinpoint this laser, but the application of this kind of unstable cavity is for high power stuff. So high power, where the beam profile is not important, power is important. So the beam profile is annular type, okay? You cannot use for certain experiments, okay? But this one has high power. Second configuration is negative branch confocal resonator. In negative branch confocal resonator, both the mirrors are concave mirrors. Difference is that one of the mirror is smaller in size. One of the mirror is smaller in size. So what will happen? The same thing like in the previous case, light will come out, but not through the mirror, but from around the mirror, because the size of the mirror is smaller than the other size. So the same beam shape, annular type, but it's powerful. Here you can see maximum use of the gain medium, fulfilling. Here is also maximum use somehow, not that much in the previous case, but still. So the extreme high efficiency, extreme power you can get in this case. So unstable cavity is suitable for this kind of stuff where we need the power. We are not concerning about the beam shape. The power is the main concern. And what other properties it can be? Definitely these resonators are not stable. Okay, you cannot apply that formula here. The light is not trapped for a long time. Okay, and or not for many trips. Few round trips and then go out. Suitable only used for high gain lasers. Okay, high gain. If you have a gain medium, which is having high gain, then you can use. Here you can see, I mean, it's animated form of this kind of unstable resonator. You can see here. And as I explained, this one is concave, this one is a convex, this one is concave, this one is concave, smaller size. The beam is coming from here, here, and from this side also, if you show 3D. Okay, and you can see here, these rays are passing through, but do not pass through the medium, but it passes through around the mirror in both the cases. So that at the output we get kind of annular kind of beam. So this is unstable resonator cavity configuration, the two most popular categories, and it's used for high power stuff. Okay, some primary benefits, and it may also have some disadvantage as well. Okay. First thing is that, as I mentioned, that we don't use any kind of partially polished mirrors in this one. Total reflectors here. And that would not be damaged because light does not stay for long. But even in this case, it has some special coating to sustain the high power. Okay, in the tens of kilowatt or this kind of the power if you need. There is no output coupler, and one of the advantages is utilize a large volume of the lasing medium. Here you can see almost covering full. Okay, and this is very efficient extraction of the energy from the gain medium. Okay, and disadvantage, actually the beam is not Gaussian type, and the beam is annular type, so it cannot be focused on a sharp point, obviously. Okay, because there is nothing inside of it. It's hollow from inside. Okay, but still it has use where you need power, and probably you cannot use this one for the cutting maybe, but it has some other uses related to the defense class lasers. Okay, so this is a famous KFT stability diagram. You can see in most of the books. What values we have calculated, the product of G1 and G2. On this basis, this one is strong. So we get the product of G1 and G2, 1, 0, whatever it is. So this is this is your x-axis, this is your y-axis.
Papantlita.
Negative x, negative y.
Bebé.
Here. And what G values are here, and what G2 values are here.
Pásame el papel,
Different.
ándale.
Okay,
Ese
we saw
papel.
0, 1, 2, 0, 1, 2.
Por favor.
So this shaded portion here, this is a stable portion. If the product of G1 and G2 comes in this region, it's stable. This region, stable. This region, unstable. This
Agárralo
region,
de allí
unstable.
porque se te va a caer todo. Agárralo de
And
ahí. Ándale de
even
ahí.
on the edge here, it will be stable. And here, also
Gracias.
stable.
Gracias, güey.
But outside is unstable. You can see on this side. So, hemispherical, the value comes here, something like 0.33 or something like this. Okay, so it's stable. And here, plane parallel, it's come on the edge, 1 probably or something like this. This is also on the edge. And concentric on the edge, confocal around the 0 value. Okay, so it's categorized stability. And here you see concave, convex. Okay, stability is 0.55. So you can see here. So it's exactly in the region of the where you have a stable the KFT region. So this one, with the help of this diagram, you can understand which cavities, the edge, which cavity can be stable, which cavity cannot be stable. Okay. Now, the beam waist. This is also part of the cavity optics. If you see here, the beam, this is the cavity here, the cavity mirrors. And somewhere here, the beam is minimum, beam waist is minimum here. We call it, this is the portion we call the beam waist, the minimum radius or the diameter of the beam. Okay. And this is very important to calculate to find out what will be the beam profile at the output. So and the output comes out, this is a perfect Gaussian. And this is like this. And you have this perfect beam profile. Okay. So the beam waist, basic formula for the beam waist, and is this one. Okay. Number of ways, I mean, there are, the people can define this beam waist. Like first point here, the beam converges at the center of the gain medium. Okay. It's called the beam waist, and it's rotated by the omega naught, W naught. And also this is the smallest spot size of the beam. Smallest possible spot size of the beam. So beam waist, the beam waist, if you see in the formula here, is directly proportional to lambda and also directly proportional to the length. This 2 pi is a constant thing. Okay. So if the wavelength increases, the beam waist increases. And if length increases, then the waste will also be increasing. Okay, so it's a directly proportional. Why we need the beam waste? Beam waste is necessary when we design the cavity. We have to measure the beam waste. We see the quality of the laser beam. We use a CCD camera. We use a CCD camera in the cavity to see and measure the dimension of the beam there. And then we calculate and something like that. Okay, so and we already studied the divergence. Divergence is what? Spreading of the light, okay. So laser has a very less divergence as compared to the white light, normally used light. And formula for this one, if you remember, is theta is equal to lambda over pi omega naught. So what is the link between the divergence and the beam waste? Here you can see the theta is inversely proportional. Theta is inversely proportional to omega naught, the beam waste. So if theta is increasing, beam waste will be decreasing. And if theta is decreasing, beam waste will be increasing. Okay. So, and last, if you see here this box, the shorter the wavelength, so the shorter wavelength mean like UV, blue light, and UV also have like 200 nanometer to 300, something like this. Shorter wavelength and larger beam waste, or like they have a tendency to collimate and ideal for pit size cutting. Shorter wavelengths, not the longer wavelength. Longer wavelength is the red, infrared. Shorter wavelength, we're UV. Okay. And the pinpoint focusing of this kind of focusing and collimation of this kind of shorter wavelength lasers are much more efficient as compared to the longer wavelength laser. And this is because of the waste stuff. Okay, so now we start with the next topic, which is probably 15 minutes more, maybe. Yeah, I will not cover fully, but introduce somehow. What do you see in this slide now? Standing waves in the cavity. These standing waves we discussed in the last lecture. And standing waves are generated, moving to and fro. And when the waves are overlapping, the resultant waves come out. That is constructive interference. That is coming out of the cavity, cavity mirrors. And the waves who are having destructive interference, they are canceling out each other and nothing will come out. So what you see here, the red one is a resultant of two waves. When the two waves overlap constructively, then we get something, resultant wave, and that is what we get at the output. So there are many standing waves maybe. Okay. And how these standing waves will be spotted, we have studied in the last lecture that there are certain conditions of the length of the cavity and the phase 2 pi or something like this. Okay, so it's just a visualization of the standing waves in the cavity. If we move further now, laser modes. What are laser modes? There are two kinds of laser modes actually. First, you need to know longitudinal or axial modes along the direction of the cavity, along the axis of the cavity. Like if this is the cavity, so in this direction we have these longitudinal modes. Like you can see here in this graph, there are many waves. They are moving along the axis. Okay. Now, the first point, if you see, a wave of frequency nu travel along the axis of the cavity and forms a series of standing waves within the cavity. Series of standing waves within the cavity. It may have same phase or maybe different phase, it depends. So the laser modes basically governed by the axial dimension. It's because of the axial dimension of the cavity. Axial, x-axis, okay? So that is why it's called longitudinal, because it's along the length of the cavity, and or axial modes. If you see here in this diagram, there are many waves here, small you can see. These are in the cavity. Some are overlapping, some are not overlapping. Okay, we cannot suppress in a simple way. So we have to compromise. There are many, so we call it modes. How many different colors are existing here? Different wavelengths, different waves. We call modes. Mode 1, mode 2, mode 3. This is modes. That is called longitudinal modes or axial modes. So these axial modes are always there in the cavity. And in case of a normal standard laser, I mean, we need like a single wavelength, ideal case. So these modes are kind of disturbance. We don't need the modes. We have to suppress some modes. We have to remove some. But in case of ultrafast laser, we need these modes. Okay. Now, if you move to the next slide here, you can understand when the two modes
Mira, te voy a regalar esto.
overlap each
Es
other,
un pizarroncito para mi Kissy, para que hagas
a resultant
sus
wave is produced, which is a
Está
green
chiquito
one,
como tú. Y ahí
and
puedes
that green
escribir,
one
dile
we
a
get
mamá
at
que
the
vas a
output.
escribir. Y se borra,
But
mira.
there are some other
Lo que
modes
escribas aquí se puede
which are
borrar.
not overlapping each other. They will cancel out, or maybe they are not
Ve a
overlapping
escribir, ándale en tu
like with the
pizarrón.
same difference, phase difference. Okay. So there are many modes. Some modes they can produce the resultant wave. Some modes may not be able to produce. Okay. Here, if you read this one, if the two waves component of standing waves are of the same wavelength, like the red and blue, the standing wave looks like the green one of the two waves component. Okay. red and green, then the standing waves produced because of these two is green one, which we take it at the output of the output coupler of the cavity. This is just an example to show that two modes only or something like this. So longitudinal modes basically, it's along the length of the cavity, the axial direction of the cavity. And these are basically standing waves. There are many standing waves, okay? And we know that the length between the cavity is L. And we have studied this formula the last lecture, probably the resonator, not in the resonator, cavity. Yeah, resonators kind of stuff. And M here are the number of modes. Okay. So we can convert this one into the frequency. We have like this one, that nu is equal to MC over 2L. To find out the number of modes, okay? Or to find out the frequency if we know the modes and if we know the length. So okay, so the distance between the cavity mirrors is L, and the condition for a standing wave in the cavity is this one. We know already, okay? The number of waves inside the cavity is an integers, okay? These are standing waves inside the cavity, integers numbers, okay? That we have studied in the last lecture, okay? So all the other wavelength who doesn't follow or doesn't satisfy this condition, they have a destructive interference and it will be extinguished. The waves who satisfy the condition of this one, they will come out. So these resonant wavelengths actually are basically the longitudinal modes, the resonant waves in the cavity, and are spaced apart at a regular interval of frequency, this one. Okay. There are many modes here and we get a resultant mode. This is just to animate and show what exactly is going on in the cavity. So the longitudinal modes here is the formula for, if you go back to the previous lecture, standing waves in the cavity satisfy this condition. The equation of frequency, this is the refractive index here, M number of modes. In some places, M is written like N, okay? And M is the number of half wavelength of axial modes. If you go here, this is, okay? And each value of M defines the axial mode of the cavity, each value of M. So in this figure, the two waves are shown, okay, the two modes here. But if you remember in the last lecture probably, the gain of the medium is also important. How many modes can be in the gain of the medium? So if we have, this is the gain curve, these are modes, okay? So it depends how many modes can be inside this gain medium curve, especially at the peak. So that will be amplified more. So the difference separation between these modes is C over 2L. C over 2L. And this one is a threshold. Below this one, there will be a mode, but that will not be amplifying. Only this portion will be amplifying. Here in the animation, you can see this one is a main one, the peak, main peak, and this one also somehow amplify, this one also, but the rest will not be amplifying. So you get spectrum like this. You don't get line spectrum because still there are some modes, some other wavelengths are existing. Okay. And the separation between these modes is called FSR, free spectral range. This mode, this mode, this mode, okay. The separation between these modes is called FSR, free spectral range, okay. And this is this formula, which is similar to this one, only M is removed from here. So FSR is equal to C over 2 pi, not 2 pi, mu N. So the frequency separation between the adjacent modes here is FSR, okay. And all the axial modes contribute to single spot of light in the laser output. All the axial modes contribute, okay. So that is why we have a spectrum like this, contribution, okay. If only one mode, if we could have, then that would be a straight line, ideal case. So coexistence of multiple modes reduce the monochromaticity and poor coherence. So we cannot eliminate other modes, but we can minimize some of these modes, okay. So in normal lasers, these modes are, we try to minimize the modes, but in the ultrafast laser, we try to have more modes, a broader spectrum, okay. So these modes are important. In the ultrafast laser, we lock these modes. In normal laser, in the normal laser theory, we have to eliminate these modes. Okay, so move to the next slide. Here, similar kind of things. I mean, like here you can see the cavity here, and this is the frequency spectrum. If this one is one of the wave, which is a mode B, and this one is A. So if you see in a spectrum here, this black one, not the dotted one, this one actually corresponds to this one. And this B corresponds to this one. And there will be a C as well, which will be correspond to some. Okay, so these modes are oscillating inside. Okay, and at the output, we get some contribution from all these modes. Some modes are poor and some modes are very prominent. Like if you go down, these modes will be contributing very poor or maybe eliminated. So we get the spectrum like this. Okay, and so it shows the two different modes and distinct the longitudinal modes. Definitely it has a different wavelength. Here, similar kind of thing which I have shown you before. There are two longitudinal modes, okay, and we have a resultant of two. And this resultant of two will be will go out of the output coupler out of the cavity, okay. And these are like this one is correspond to this black, the peak. Okay, so this is You people already, I mentioned this thing in the previous slide as well. The gain curve, number of modes, cavity resonance, you can say, and output. In the cavity, there will be so many modes, so many wavelengths, okay, adjacent to each other. Okay, we want one wavelength, okay, 520 nanometer or whatever it is, but still there will be other wavelength existing. Number of modes are there, and the number of modes, all the number of modes will not be amplified, and only those modes will be amplified which can come in this the gain curve, in simple words, okay. So like this one, but still there are 11 modes are there. Still 11 modes are there. So 11 modes, it can be like, if you have 520 is a peak, then it can be like 521 and 519 here, 522, 518 or so on. Very close to each other, adjacent. Okay. So here in this animation is this thing is shown that this is the gain curve here, okay, and then these modes are appearing, and only the modes which are inside the cavity, inside the gain curve, that is only amplifying, and we contribute, these modes contribute at the output of the laser beam. Okay, so these were the longitudinal modes, and longitudinal modes are important. Other modes are called transverse mode, which we see in the next slide. Oh, sorry, next lecture, not the slide. So today's lecture, I will conclude here now, the longitudinal modes, and we will also study how to control the longitudinal modes in general purpose lasers. Okay, in the ultrafast, we need to have these modes. In normal laser, we need to eliminate these. Okay, so this is how the longitudinal modes are working or existing, something like this. So that's all for today. If you have any question, and if I can understand your question, I will be happy to answer you. Only few people are here. People are coming and going. I don't know. So David, you have a question?
In this last slide, FSR is equal to free spectral range?
Yes. C over 2L.
Okay, thank you.
C over 2. This one. Here. Okay, so anyone else? Nargas, did you understand?
Little bit, but there wasn't a flow for me. So I think when I will revise this lecture, then it will be helpful for me.
Yeah, sure. Okay, and how about Fatma Noor? Ruta? Salman? All the people are sleeping, or what exactly it is? Tahura? Ali Hasnan?
Sir, I did understand.
Yes, sir.
Fatma Noor, you are, I don't know, it's messing up. Anyway, Ali Hasnan.
Yes, sir. Assalamu alaikum.
How do you feel about the assignments? I mean, you submit very late.
Actually, I am a repeating since last week, and also on vacation in a very backward area where there is no internet connection or sometimes very weak internet connection. And I forgot my laptop at my home. There was no laptop, and I thought I could reach home and made that on laptop, but couldn't reach home. So I found a pen and page and wrote it on that.
Okay. It's okay. Okay. And yes, Fatma Noor, we can hear you. If you want to say something, you can.
Sir, nothing in particular right now, but I do have a question which I'll like go through this video again and then form the real question about the spot size and the size. You were explaining it. My internet was a bit weak. So I had a question over there. I'll clear that question and send you, okay?
Okay. Sure. Okay, Mauricio, how's it going?
Well, it was understandable. I have no questions for maybe thinking about it later. I could have a question for next session.
Okay. Sure. Okay. Ihtisham?
Currently, sir, I don't have a question, but I was just a little bit confused about the unstable resonator in which the middle part of the beam was blocked. So how can it help in power increase?
Which oscillator? Oscillator or resonator?
A resonator, unstable resonators, in which we get the annular shape of the beam at the end.
Yes. So what is the question?
I mean, why it was the middle portion of the beam is blocked? I mean, it has a very high gain media, so
because it's unstable. It's if the gain is very high, if we make a stable kind of cavity, it will burn. Okay, so that is why we have unstable one. So this beam actually it's hollow from the center. The second mirror is a very small size. Here I'm showing you, it seems big, but it's very small size.
So it's not contributing into the amplification of the light?
It does. I mean, only few passes. After a few passes, go out.
Okay.
So this is the purpose of this one. Gazanfar?
Oh, thank you, sir.
Yeah. Gazanfar?
Yes, sir.
So you are sleeping? I mean, you complete your sleep?
No, no, sir. I am listening. Sir, can you move the next slide? I am confused in that also.
Which one?
Next. Where? Yes, this one.
Yes.
I am confused in the left side of the figure.
Which one?
Sir, this
left side.
Yes, left side.
Yes.
Maybe I will.
You go through and see these cavities. I mean, you can calculate even.
Okay.
But your concern should be now it's modes. Okay, because ultrafast laser is modes and mode locking.
Yes, sir.
You know the mode locking?
Yes, sir.
Yeah, a starting point.
Yes.
So
Q switching is also this.
Yeah, Q switching actually cannot produce a very short pulse. Okay, Q switching is for the giant pulses, but it cannot produce a very short pulse. For the short pulse, you need a mode locking.
Okay.
Okay, so with the Q switch, we will study Q switch actually. Maybe at the moment, I think nobody understand what is the Q switch here. So Tahura Hadi and Arusa Hadi, you people can listen to me? And how about you people? I mean, feeling about your feelings about the people, or it's a bit tough, or time is short, or what? If you have any, I mean, feedback, any of you? No reservation? No problem with the assignments?
No, sir.
David, it's okay, the assignments, or is it difficult, or is easy, or what exactly?
It's okay. I need to investigate some of the formulas for the second point of the homework, but the other is more about reflection of what you understand about the process, like gain and amplification, and why we need to pump in a cavity to get the laser action. It's they have incremental difficulty about the first homework and the second, but I think we study after the lecture. We can complete the homework without problems. Thank you.
Okay, that's good. Okay, and also you people must have known that these lectures are also transmitted live to the YouTube and the Facebook. Okay, so if sometime you people are somewhere, you people can listen as well. You may not ask the question, but you can write the question there. So it is probably is a good thing. So I mean, if there is no question, then probably we will meet next lecture. Okay. So thank you very much for attending, and see you on the next one. Yes, Tahura. Any question?
Yes, sir. Assalamu alaikum.
Walaikum salam. Yes.
I have a question.
Yes, sure. You are listening. It took a long time. Yes, sure.
Can you hear me?
Yes, I can hear you.
Sir, is the cavity length play any role in determining the longitudinal move?
No, I
decrease
can't.
or increase the cavity length. So, is there any effect on the longitudinal mode?
No, I cannot hear you properly. Your voice is like it's coming in the parts. Can you repeat your question? I think net is not very efficient there.
Net is sir, is the cavity length play any role in determining in the longitudinal mode? When we increase or decrease the length, cavity length.
Definitely, there is definitely. So your question actually, it will be answered in the next class when we study that how to control this, the longitudinal modes. How we can control these longitudinal modes to some extent. Okay, so we cannot reduce the length of the cavity as such, because length of the cavity is calculated according to the wavelength, what wavelength we want. But we can compensate some of the modes by some other techniques, which we will study in the next class. Okay, Tahura?
Sir. Yes, sir.
Okay. It's good to ask the questions actually, but your net is always having problem. I don't know. Okay, guys. Then thank you very much for attending, and let's meet on the next class. Okay, thank you very much. Goodbye to all.
Thank you, sir.
Thank you, sir.
Goodbye.
Allah Hafiz.